Let's now talk about the concept of irrotational fields. So a vector field F is called irrotational when the curl of the field is 0. The reason for this name is that the curl, some people call it the rotational of a field. So when the rotational of a field is 0, then the field is called irrotational, meaning it doesn't have a rotational. Okay? So that is a very simple definition. Are there some physical examples of irrotational fields? Actually, yes. Example, the gravitational field. Once again, gravitational field G is irrotational, which means that the curl of G is equal to 0. Okay, so for example, for a point mass, so this is true always for any set of masses, like in the solar system, you have a complex gravitational field, but its rotational is 0. But in the specific case of a point mass, when the gravitational field is given by minus gm divided by r squared er hat, then the rotational of that is 0. And it might be an interesting exercise for you to check that. So if we try to picture this, what's going on? So you know that for a point mass, the gravitational field looks something like this. And then it gets weaker as we get further away. But clearly, if you look at this, there is at no point would you say that this field is rotating, right? Sorry that I was blocking. So a gravitational field never has like things that rotate. So the rotational is 0. It is an irrotational field. Okay, so what's so special about the gravitational field that is conservative? It's also irrotational. Why is that? It's actually not a coincidence. So let me write this important theorem that if F is conservative field, which means F derives from a potential, then F is irrotational, which means that the curl of F is equal to 0. Okay, so if a field is conservative, then it is irrotational. Let me prove that to you. So let's call this 1. So proof of 1. If you calculate the curl of a field, and this field happens to be a conservative field, you can substitute F by the minus gradient of phi. So we can take the minus outside, so this will be the minus curl of a gradient. And if you remember our list of mathematical identities for divergence, curl, and gradient, what we saw is that the curl of a gradient is always 0. So this is equal to 0. Okay, so we proved that if a field is conservative, it must also be irrotational. So that's why the gravitational field, being conservative, is also irrotational. The electrostatic field is conservative, and therefore it is also irrotational. Now more interesting is to consider the proof the other way around. So this is true almost always, but not always. And I'm going to put an asterisk here. So if a field is irrotational, so I give you a field whose rotational is 0, do you immediately know that this field is conservative? It depends. So this is true only if the field F is well defined on a closed region of space, or mathematically speaking, on a simply connected region, which means that it has no holes in normal language. So for example, if a field f is defined in a region like this, and the rotational of f is 0, then you know it's a conservative field. But if the field f is defined in a region with a hole, okay, so you only define the field on this region, then there is a hole, and therefore the theorem is wrong. So here the theorem, this line holds. Here, yes, it does hold. In this case, it doesn't hold, okay? So one typical example would be the magnetic field created by a line current, which at the point of the current goes to infinity. So it is not defined at the point of the current. It's only defined around the line current. And around the line current, you can see that the rotational of the magnetic field is 0. However, the magnetic field is not conservative because there is like a hole in the middle of the region where you are defining it. Anyway, this is, I would like to say that this is not important for this module. It's just that since I was teaching you this theorem, I had to write this asterisk because I cannot teach you something that is wrong. Okay, so initially I was just going to write the double arrow, but then I said, well, what if when they are in year 2 they get confused because they thought this was true and suddenly it isn't. So that's why I added this asterisk. Okay, but I would say that this asterisk is outside of the current module. I'm not going to ask something related to this in the exam. Okay, it's just for you to know. Excellent, thank you very much, and see you in the next video.